All right, so the last couple of days we've been talking about uniform circular motion. Okay? Objects undergoing uniform circular motion travel in a circle because they're always accelerating where? Towards the center. Okay. And they're always accelerating towards the center because what's pulling them there? Yeah, a centripetal force. It could be a string, it could be gravity, it could be friction, whichever. We've talked about lots of different things that act as a centripetal force. Today's lab is actually going to be a bit of a step backwards in that we're only going to be investigating this formula. 2 pi r over t. We just want to confirm the relationship between the radius of a circle, r, and the speed at which the object moves. Okay, everybody follow me there? All right. So in this lab then, we're going to be using an apparatus kind of like what you see in that picture. Okay. They're these highly technical things that Mr. Dickey and myself built. Okay. And so they're a tube, and they have a string run through the tube. And on one end of the string is a rubber stopper, okay, and on the other end of the string will be a mass. Okay. What we're going to be doing is testing how fast does an object move based on how big the circle is. Okay, so as the circle gets bigger, what happens to the speed of the object? Okay, so that's what we're going to investigate. Okay? So what we're going to be doing then is taking different radii. So our first one might be like 20 centimeters, and then 30, and then 40, and then 50, and then 60, and so on. Okay, and we'll be whirling them around and around in a circle. Right? Now, we can't measure the speed of this rubber stopper directly. We'll have to calculate it. The thing we can measure directly is how long it takes for it to go around the circle one time, which is called the what? Period. Okay, so we're going to use the period here in order to calculate the speed of the object, which means there's probably more than one responding variable here. Okay, because as I change the radius, according to this formula, this number and this number should what? They should change. Okay, that's what we're kind of looking at here. Now, we know that there's other things that can affect the speed of an object moving in a circle. Okay? And one of those things is the force that's pulling it back. If I increase that force, will it change the speed? Yeah, it will, okay, because we learned this formula just the other day, okay, that says that Fc equals mv squared over r. If I change Fc, that's going to change v. All right, so I want to make sure that that centripetal force stays the same. What's providing that centripetal force here? Don't answer, just look at the setup. There you go. Okay, so something is providing a force that is going to keep this thing traveling around and around a circle. Everybody okay with that idea? All right. There may be some other things that need to be controlled, okay, as we do this. Now, I'm going to show you the technique here, because the technique is a little bit tricky. If you feel like you would like safety goggles for this lab, I will go across the hall and get them. I've only ever had one person get a shiner doing this lab. Okay? Only once. I mean, I've had people hit themselves in the head with a rubber stopper. So, it's not like you're going to give yourself a concussion or a skull fracture with this rubber stopper. Okay? Keep in mind that it is the rubber stopper and not the weight that should be circling. Okay? That can be a problem. Okay? We do not want the big metal chunk here to be whirling around the circle. Okay? So, the key to doing this right is that we need to make sure that the radius of this circle stays the same while it's being whirled around and around. If it changes, then it's going to change the speed at which it moves. You can't hold the string. Because if you hold the string, what are you doing to the centripetal force? You're changing it. You're providing more things for the string to pull against by stopping the string. So you have to achieve this delicate balance that results from, okay, I'm whirling this thing just fast enough that the radius doesn't change, and that I'm not holding the string. So you can see here there's a little mark. I don't know if you can see it or not, but there's a little mark on the string here. I'm just going to get it right to the bottom of the tube. And then I'm going to do my best to keep that mark right on the bottom of the tube. Then I know that the radius isn't changing. And I just whirl this around and around in a circle. And I have to watch it. Okay, I got to do my best there. If I go any faster, look what happens to the radius. right? Suddenly the radius increased. I don't want that, okay? And you can't just slow down now, okay? Now you have to start over by pulling this thing back down, okay, to that initial mark and starting over again, okay? Now, look at where I've got this thing, okay? See how far above my head it is? There's a reason for that. First off, it won't hit me in the head. That's the most important reason, okay? The second reason is I can see the little mark on the bottom that I've made on the string to mark the proper radius. If I make that mark up here, how hard will it be for me to see? Very hard, unless I do this, which will work as long as my radius is longer than my arm. P.S. One of the radii is longer than your arm. Okay? You will get this in the face if you do it that way. Okay? Now, the other thing is, I want to make this as horizontal as possible. Okay, because we're trying to deal with uniform circular motion. If I start doing this, okay, I change the type of circular motion that's going on. Notice how the speed of the rubber stopper changes now. Okay, bottom of the circle it goes faster, top of the circle it goes slower. I want a nice horizontal circle. Okay, so I want it like this. All right, everybody okay with that? That, by the way, is the technique to end the experiment. Okay? Don't just slow down. It'll get you in the mind. Okay? We don't want that. All right, so we're going to be, like we said, recording the period. Now, we're going to time more than one rotation because we want to have fairly decent accuracy. So when you're recording your stuff, you're actually going to record, I think it's 20 revolutions. Okay? So you're going to do 2 trials for each radius. You're going to average those times, and then divide that time by how many to get the period? 20. Because this is the time for 20 revolutions, and we want to have the period, which is the time for 1 revolution. Okay? So this involves having pretty much everybody in the group be busy. Okay? One person's entire job is whirling the rubber stopper. Okay? That's their only job. It requires all of their concentration. Okay? It requires all of their concentration. They can't be counting, and they can't be timing. In fact, that should be 2 separate people. One person timing, one person counting the number of revolutions. Right, so you need at least 3 people in a group for this to work. Okay, and then you'll calculate the speed. Okay, here using v equals 2 pi r over t. Right, then you're going to do the rest of the questions after that. All right, so we've talked about the design already. Okay, in terms of our hypothesis, okay, we want an if, and then statement talking about the relationship between radius and speed. That should be your if part. The and part will describe the experiment, and the then part, tell me what's going to happen as radius increases. Okay, so then as radius increases, speed will blah, blah, blah. Okay, everybody clear on the hypothesis? Okay. So procedure, like we said, pretty straightforward. You know what to record. These are going to be our radii, except you're probably going to want them not in centimeters, but in meters. Okay. And then, like I say, make sure when you're doing that, okay, so when you're measuring the radius is measured from the edge of the tube. Put the mark down here. Okay, so here's a radius of 20 centimeters. Okay, I put a mark down here that I can watch. Okay, that's my 20 centimeter mark. Make this 30, put a mark down here that I can watch. Everybody okay with that? All right, so you're going to be doing this up to 60 centimeters. Make sure you give yourself enough room. Okay, I have had groups like get their stoppers tangled, and it's a horrible mess. We end up just cutting the string and starting over. All right. Then for your analysis, okay, the analysis is pretty straightforward. A lot of the questions are just filling in the chart. Okay. It starts getting more of the kind of higher level stuff when you get to question 4. Identify the force that acts as a centripetal force and determine its value. Just as a tip, you will not be using mv squared over r to do that. Okay, that is not the formula that you will use to answer question number 5. Okay, question number 4. For number 5, plot a graph of velocity versus radius. So get a Google Sheet. Okay, I didn't provide one this time. You can just make one. All right, remember the first column is your manipulated variable. Second column your responding variable. Build the graph. Okay, and then from number 6, what's the relationship between radius and speed? Explain. Okay, make sure you explain your answer. All right, then conclusion and evaluation, same as it's always been. Questions on what we're doing? Okay, so get together with your group, come up and grab the equipment you need, 1 box of weights, okay, one of the circle things.